Hello, everybody, and welcome to physics. Now, specifically in the context of this video and this series, welcome to CBSE's physics for the 12th grade. Now, why am I teaching this? Why did I decide to make a series about it? Well, quite frankly, it's because I studied this and I studied, CBSE's physics in the 11th and 12th. And the general idea was, physics is hard, it's dry, you don't know what's going on, or maybe you do, study a few repeated questions, a few derivations, practice the questions, and you'll be able to score well, maybe above a 90, right? And I'm here to tell you a few things. Now, first of all, uh, well, it's not hard. It's pretty easy actually. The concepts within the physics textbook are pretty easy. It's just introduced and taught in a difficult way, I think. And maybe the mathematics is a bit tricky, but that's about it. And I'm a firm believer in the idea that if you know the concept very well and you have some solid math, you'll be able to solve anything. As long as you understand what the question is trying to tell you, what they're asking, you should be able to solve it as long as you have the data. And they are supposed to provide you the data because you're guys in school. Now, a little bit of background about me. I am currently an MSc student in electrical power engineering. I'm done with my bachelor's of engineering, and currently, I'm an ongoing student. I still go to university, and I had started this channel initially just so I could maybe make a few videos about what do I do in the uni, or maybe to teach a few concepts that I find hard to understand. So I could get a better idea of what's going on. But recently, I had to meet one of my old classmates from high school, and he told me that his brother, who's in the 12th, is still, facing the same problem that everyone else did with physics, and he has to, struggle in a way. And that's when I realized, maybe I should do something about this. And that's where I decided to start it. Now, within this series, I'll just be trying to break down every single concept that's described within the CBSE's 12th grade physics textbook and explain the essence behind it, right? Well, we'll be doing a few questions here and there, yes, but it really isn't as hard. It's not that deep. It's as long as you guys have a firm understanding of reality, it's okay. Well, physics can explain everything. It could explain why maybe this cup that was once hot because it was filled with hot coffee is now cold to the touch. It could explain why this calculator here works, could explain how this headphone that's wireless is able to transmit the data. It could explain all sorts of things. And I believe physics comes naturally to everyone. You see someone pushing a car with, I don't know, a distance of a meter, and you see the same person maybe push a pen across the table for 1 meter, you obviously know that he spent a lot of more energy while pushing the car. And, we don't have all the time in the world to sit down and write that, so we've developed simplified notations to do it. Now, behind me, there's that equation. W is energy or work, X is the distance, divide work by the distance that the force is applied on, and you get the force. But if you write down this way, it looks slightly more intimidating than me telling you, hey, if I push something for a longer distance with the same force, it's going to require a lot more energy. It's obvious. I don't need to tell you that. But writing it this way makes it a little, I don't know. It depends. Maybe a bit more complicated. So let's begin the essence of physics. I will teach you the concept. I'll break it down to its simplest level. I'll try to explain it such that anyone with a basic understanding of maybe reality and some basic math would understand it. And if in case in some video I've made it a bit complex, I've not made it simple enough, or it's hard to understand, please let me know. Immediately I'll try to correct my mistakes and make it simple for you. The whole objective of this is for everyone watching this to just understand it from scratch and to not worry. right? We're doing this to understand physics. It's not, well, if you want to just pass an exam, it's also possible. But the idea is it's just for the love of physics and to understand it. And that is all. Thank you. Now, let's examine what it is that we have to study, right? So we first have something I'd like to call the map. Okay, now this map, well, the map of grade 12 physics. Now this is pretty important. Now this would kind of give you an idea about, well, have you ever thought about why your textbook is built that way, right? We've got two textbooks, right? I'm just going to focus on the first textbook for now, right? The one with more chapters. And here I'll be talking about what have they really done, what's caused their decision to make this particular textbook in the way that it is, right? So first we've got, well, chapter 1, that is electric charges and fields. That's the whole thing, electric charges and fields. Now, they're going to teach us from a very fundamental point of view, right? What is an electrical charge? It's just a charge. It's just something. Now, we haven't been able to define what exactly a charge is, just like how we don't have a definition for what mass is, right? Well, I could say 1 coulomb of charge or 1 electron. Now, what is charge? Well, we don't know, right? We could say it interacts with an electric field. If I bring an electric field, the charge would either attract or repel. But we have not been able to say more. We know that there are a few elementary particles with charge, but we don't know what charge is. But that's why the first chapter starts from the fundamental. You technically can research on what charge is and go into the particle physics behind it, and you still may not get a satisfactory answer depending on what really satisfies your question. But we're going to start from that. Electric charges and fields. Just the bare basics. Now the second chapter is almost got it. Now it's just electrical potentials and capacitance. Now, what is this, right? So the first thing is there's a charge, right? There's a charge and there's a field that the charge produces, or there are fields and the charges interact with them. That's pretty much the basic. Now, electrical potential and capacitance. Now, potential basically is just that when there's a field, there's a region of higher potential, there's a region of lower potential, and a charge would likely want to go from a region of high potential to a region of low potential. Now, well, you could see this charge here. If I place a tiny little charge that can't affect this charge here, this is some region of high potential. It would not want to be here. It would want to go away. It's similar to having a battery, right? If the current would want to flow from this terminal to this, because it's a drop in potential. It's like water flowing from the top of a dam maybe to the bottom, because there's high potential there. And capacitance is something that we would examine in detail. It's caused by, we'll need to understand potential first before we get into capacitance. So there's two things. There's a strong field between them, which gives a pretty good potential difference. So that leads to the formation of something that we'd like to call capacitance. And this is pretty useful later on if you're going to analyze circuits, because, well, in any electronic device, capacitors are everywhere. Trust me, they're everywhere. Even if you're not an electronic person, if you want to do something electrical, it's still everywhere. You can't escape it. And it's pretty simple. As long as you understand potentials, you'll be fine. So it works that way. If you understand number one, you're prone to understand, well, if you understand charges, you would understand fields. If you understand fields, you would understand potential. And if you understand potential, it's highly likely that you would understand capacitance. Moving to the third chapter. Now, this is a big one right here. I hope the spelling's right. Electricity. Well, there's a bit of a difference, right? The first two chapters, right here, are talking about electrostatics. Now, electrostatics is a sort of phenomenon where the charges are, well, in space, in a vacuum, or maybe in a medium, but they are charges, isolated charges and fields. These are, well, not things that we would encounter on a daily basis. Well, I could say if you have a mosquito bat, right, that is used to kill mosquitoes, you could see that there's two layers, and then a mosquito gets in between the two, and it just has current passing through it. Now, we could say that there is some sort of, let's say, field between the two that's causing it. Or even a better example is if you've rubbed a plastic ruler through your hair, you could attract some pieces of paper. It's all electrostatic. The current electricity it's something that we use even more commonly in our daily lives. It's just, well, current, the light, well, the fan, every household appliance that you'd use. Now, what sets this apart? If you have a conductor, right? A conductor is something that can conduct electricity. We'll get into the details of it later, but maybe a copper wire. If this charge, instead of being in space, that is stationary, or maybe it's just moving as an isolated charge, if a bunch of charges, now I've done positive, you know that electricity is negative because electrons are negative. We'll get to that in the third chapter, but if a bunch of currents are flowing through a conductor, it is now current electricity. And we'll be examining its properties in the third chapter. We will deal with things such as, well, drift velocity, Ohm's law, Kirchhoff's law, and pretty much a lot of circuit analysis related thing. Now, moving to the fourth chapter. Moving charges and magnetism. You know what? I just write down the fifth one as well. Magnetism and matter, and moving charges and magnetism. Now, when electrons or current passes through a wire, it produces a magnetic field. It just does. It produces a magnetic field around it in more details that I would examine when we get to that chapter, but you might know the common experiment. If you have a compass, if I have a compass, a magnetic compass, and I have a wire, and I turn on the wire, well, a circuit, and if I let current flow through the circuit, it's going to deflect the compass. It's sort of to say that it produces a magnetic field. When there's a charge and it moves, it produces magnetism. That's what we have here, moving charges and magnetism. And in the fifth chapter, magnetism and matter, we'll be examining a few of the things. Some things are pretty common between these two. The last word's the same here, but matter. Now you might be asking, well, what about a permanent magnet? Right? I broke open my oven, my microwave oven, there's a magnet there. Or I bought a magnet from the shop. And it's a permanent magnet. Now, am I supplying current? No. So there should be some relation between the two, right? Well, it's not like inside of it there are small wires that are causing this current. No, it's not. It's just a stone. It's just a rock. It's just something. It's a substance. We don't know what it is. And that's what we'll be examining here, right? Now, in this we would examine poles, North Pole and South Pole, something like that. And it's pretty similar to the first one because poles of a magnet are pretty similar to electrical charges. So instead of having electrical charges positive and negative, you would have North Pole and South Pole, and instead of having electric field, you would have a magnetic field. Here it's different because it's magnetism caused by a moving charge. Here it's caused by matter itself. Now the sixth chapter, this is where things get a little bit more interesting. Electromagnetic induction. Now, we had in the fourth chapter, if current moves, it produces a magnetic field. Okay, through a conductor, of course. If current moves through a conductor, it produces a magnetic field. Now, if there is a conductor and the magnetic field around it, so I've taken a conductor and I've placed it in a magnetic field, and now I've decided to shake around the magnetic field. I've decided to move it. Shouldn't that cause a current? Well, this is it, like the input here is current through a conductor and the output is a magnetic field, right? Current into a conductor produces a magnetic field. So shouldn't a magnetic field through a conductor cause current? Well, maybe not the same way. Maybe it's not exactly right to put the arrows denoting the same direction, but in some way there should be an effect, right? Otherwise it's a bit, well, it's a bit counterintuitive, right? So we'll be examining electromagnetic induction. You'll mostly be dealing with terms such as inductance, electromagnetic induction, that's the name of the chapter, and maybe an AC generator. That's an AC generator is basically what produces most of the current around you. Yep, solar panels are a thing, but well, most of it is still synchronous generators or AC generators, right? At the power station, to coal, natural gas, water dams, that is hydropower, and even nuclear, because, well, in nuclear you just heat up the water using nuclear energy, and that water still turns around a turbine, and, well, the steam actually, not the water, the steam turns a turbine, and that's it. It's just a generator. So if you understand magnetism and matter, and you understand all of this, you'd be able to understand electromagnetic induction. And if you understand electromagnetic induction, you know how AC generators work. And that's the first answer to it. How is the lights in this room working, right? Now, the next chapter is AC, alternating current. Now, a lot of people would write AC current, but it's redundant, right? Alternating current, but AC current. And in the textbook, it's written as alternating current completely. I'm not going to write the whole thing. But if you understand the concept of AC generators, well, the output that produces is AC, alternating current. So you could see how all the chapters are linked and how they're coming together to help you understand, well, almost all of electricity. Now, you start off with electrostatics, imaginary charge, not imaginary, but real charges that are floating around, to the fields, to potential, capacitance, then current, electricity, what happens when electricity moves, what is magnetism, what about permanent magnets. Well, okay, if I have a conductor and move around the magnetic field surrounding it, does it cause something? If so, can we use it, right? We should be able to. Well, AC generators, we get current out of it, and we can use that current. And then, well, we got an AC output, right? So what do we do with this? Or what exactly is it? How do we model it? How do we study it? Explained in the 7th chapter. And then, I think this is the last chapter in the book. Yep, this is the last chapter in the book. That is electromagnetic waves, EM waves. Now, if the current is alternating, right, you could say if the magnetic field, okay, the electric field, so conductor goes this way, the magnetic field goes around it, yeah. But if the electric field moves back and forth, maybe not in a conductor, maybe even in free space, if there's an electric field that moves back and forth, we've told you that a changing electric field that's caused by moving charges, right, produce magnetism. And we also know that if the magnetic field changes around in a conductor, like here, we would get induced, current, but technically it produces an electric field. That's what causes the current to flow. We know that charges move from high potential to low potential, right? So that's caused by an electric field. So maybe that changing magnetic field would produce an electric field, and that changing electric field would produce a magnetic field. So it could technically lead to a wave. Maybe this is the electric field, like that, and maybe the magnetic field, well, okay, this is up and down. I can't draw into the paper, so I'm just gonna draw it this way. What I mean is, it goes into the board, comes out, goes in, comes out, and so on. I'm just gonna draw a 3D view like that. You don't have to understand this, right? I'm just trying to. Well, the main takeaway from this whole map of physics 12th, number 1, is just to understand. Well, the textbook is trying to tell us something. It's trying to tell us that if you rub your hair with a plastic ruler and it can attract some pens, following that logic, it should produce a field, and that field should produce a potential. Now these are just, well, logic. It's just, we could observe it, we could confirm our suspicions, and we could write it down. And if you write it down in a paragraph, or if you write it down mathematically, it all means the same. So the idea is, the first chapter is linked to the second, and if you have electrical potential and you play around with it a little bit, you could understand what capacitance is. Once you understand capacitance and you understand fields and you understand electrostatics, you would be able to understand why current flows into a conductor. Well, obviously it flows, but let's take a pipe. Let's say you have a pipe. Okay? It's a steel pipe and it's used to carry water. And there's water. Oops. There's water. You've poured water into it. Now it's just lying there, right? It's not flowing. Maybe when you first poured it in, it was here, and then it just settled down, it flowed, and it's just like that now. So why wouldn't electricity do the same? Now the answer is, if you keep pouring in water from one end, it would push it, and that is something similar to potential. I could technically say, if you keep pouring in water from here, there's a high potential of water. Now potential is not it sounds like a complicated word, but it's just to say that there's a high concentration. There's a lot of pressure of water here. There's water pressure. Saying voltage is electrical pressure is, well, analogic. If you're going to cause an analogy, it may not be wrong. I don't know. It probably, electrical pressure might be something in maybe some advanced physics. I'm not sure about that, but it wouldn't be wrong to say that. Well, don't write it in your paper, because CBSE is very particular about what you write, but just to understand, I think it's not wrong. So we'll examine that in current electricity, and for that you need to know these two basics. And if you understand that current flows in to a copper wire or to some conductor, there's moving charges, and once charges move, it produces a magnetic field. We've been able to observe it, and since we could observe it, we know that something called magnetism exists. We know that permanent magnets are also a thing, because we've obviously interacted with them, and well, we used to play them. I mean, I used to play with it as kids, just north and south. I used to try to put the north and north together, and we just repel out. But well, you need some energy to have that kind of force, right? So we'd examine that. We try to understand what the difference is between the magnetism caused by current and that actually exists. There's no difference actually, but we'll come to that. And then now we know induction. Well, if the field around a conductor changes, should it cause some current? Right? It should. Well, we've been able to observe it, but it's also a logical question to ask. And what do we do with that current? That's AC. Right? We can make DC by having split rings, but I'll try to explain to you that in a second on why we don't use it. Well, it may not be in the scope of your book, or it may be, I'm not sure, but I'll try to tell you guys a little bit more, because I studied electrical power. I know why we are still sticking to AC. I mean, there are developments on DC grids are a thing, but we can still talk about it. And I would recommend this movie called The Current Wars. Now, if you guys have time, it should be nice to watch. It's The Current Wars. Now, it talks about a fight between Nikola Tesla and Thomas Edison. Obviously, you guys know who they are. One invented AC, one invented DC, and it's just a debate on what's better, right? So if you guys want to know why AC and why DC, and doesn't DC make more sense, right? It's just direct current. It makes intuitive sense. You could obviously watch this movie to see the history behind it, and I'll try to explain it further. And if you have changing current, you would have changing electric field, maybe changing magnetic field, maybe another changing electric field caused by it. EM waves, way to go. 8 chapters done. The first book, pretty intuitive. If you guys understand it conceptually, this is pretty logical. It's more than simple, just easy. Thank you. Now I'll be looking at the map of physics 2. Well, let me write that down. Hello guys, and welcome to the map of physics 2. Now, this is just concerning the second book of physics, and let's see what they have put for us here. So, starting off, we have the first 2 chapters, that is ray optics and wave optics. Now, what really comes down in these 2 chapters? Well, we have light, right? We've seen it everywhere. Light's all around us. Well, at least in this room it is. And is light a ray or a wave? Well, you've likely drawn diagrams such as this, where there's light going into a mirror, and if it goes this way, it bounces off this way, all sorts of things. But is it a ray? Well, yeah, makes sense, right? Reflection is a thing. Refraction, we will prove these things. I think we've done this in the 10th grade as well, but in this chapter we will do it again. All about ray optics. It's everything you've already studied, plus a little bit more. And also optical instruments, but I'm not going to talk about it right now. And wave optics, well, there's a few effects that we couldn't really explain with ray optics, that we could with wave optics. So wave optics says the light is a wave. Now, what's a wave, you may ask? Well, a wave is something that's periodic, maybe like that. I'm not really good at doing that, but sound is a wave. How do we know? Well, it needs a medium to travel. You go to space and then you're trying to talk. They can't hear you. You could be doing all sorts of things, but nothing, no voice. But in space, light does travel, right? That's how light from the sun comes to us. So it's a ray, right? Because waves need medium to travel, but do they? Or it's light its own medium? I don't know. We'll learn, right? That's what the chapter is there for. But I'll just give you a little bit of a spoiler. Light is pretty much both, right? Some of its effects can be explained by this. Some of it can be explained by this. Now you might be thinking, okay, so which is correct? Right? Teach me what's correct. Why are you teaching me both? I don't want to study all of this, but both are correct. That's a bit of a problem. That's a bit of a problem that physicists had to deal with. Now, coming to the 11th chapter, or the 3rd chapter in the book. Dual nature. Dual nature of radiation and matter. I'm just going to write dual nation. Sorry, dual nature, not nation. Nature. Okay. Ray optics. So I'm assuming it's pretty understood that dual talks about the ray and the wave nature, or more like particle or wave nature, right? So physicists had that problem. They don't know what light is. So there was a theory that there was the ether, which is like a supposed medium that exists everywhere, but we can't interact with it, only light can, and all sorts of things. Forgive me if I made a mistake with the definition of the ether. I'll come into more details when we learn this stuff, but we finally concluded that light is both a particle and a wave. And we did it using something called, what was it? The double slit experiment, yes. The double slit experiment. Now, then people thought, hey, you know what? I might as well write this down. Dual nature of radiation and matter. Now, with radiation, they're talking about light. They're talking about light and maybe microwaves, all sorts of the electromagnetic spectrum. Well, I mean, all sorts of wavelengths of the electromagnetic spectrum. But matter. Why matter? Well, surely my pen is an object. It's a group of particles. It's not a wave, right? I don't see it floating away. But the thing is, the question they asked is, if light behaves that way, is it only light that's a wave? Maybe not. Why don't we shoot a bunch of electrons, right? We have a beam of electrons, not to a conductor, just shooting a ray of electrons, just like that. Like particles, just poo, 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 poo. That also behaves like a wave. But we know electrons are particles, right? You know, they orbit around the atom. Do they? Are you sure? I have not seen an atom before. Well, I've seen pictures, but no one's seen it. They've just drawn it out. And they've based their evidence on experiments, right? You might have learned it in chemistry, Goldfoyle's experiment, and, you know, Rutherford's model, Bohr's model, everything of that. But we haven't seen it, so we can't really say it's a particle. So electron's a wave. If the electron's a wave, is a proton a wave? If proton, neutron, and electrons are waves, are atoms waves? I'm made of atoms. Am I a wave? No, I like to believe I'm a particle. But I'm also a wave. If my constituents are waves, I'm a wave, right? Shouldn't that be the case? If I put in a bunch of red paint into a bucket, I should observe red paint, not blue. Because I've put in red paint. It's made only of red paint, so it should be red. Well, in this case, we're stuck there. Matter is both a particle and a wave. At least that's what quantum mechanics tells us now. But who knows? Who knows where the future of physics is? I'm not a physicist. I wish I could be, but I'm not a theoretical physicist. I'm just an engineer at the end of the day. Even my specialty, my master's is also in engineering. So, we'll see. I'll teach you everything about this because I've had to study this, but I can't go into what it really is. Right? Even in your textbook, actually, if you read through the preface of the textbook, it says you can ask why as much as you want, but after a point, you don't have the answers. You have to go into metaphysics and philosophy. Well, it goes, philosophy is just physics. Well, no, the other way around. Physics is just philosophy that we can explain with math, that has mathematical proof. If you take any branch of philosophy, somehow you could convince people using math, you've made new physics. I believe so. You can argue with me, but yeah, here we go. Enough about that. Well, maybe enough about that for now. The next term, atoms. What are atoms? The model of the atom. How fast are the electrons? How much energy does it have? All sorts of things. Pretty self-explanatory. We'll get to that when the chapter begins. Nuclei or nucleuses, well, that's not a real word, it's nuclei, plural for nucleus. That is, in an atom, you have an electron. Whatever's in the center is the nucleus, like a cell in biology, but well, it's made of protons and neutrons, or maybe just protons, or maybe just neutrons. I don't know. I think it depends on the isotope, but I'd like to say protons and neutrons. I think hydrogen doesn't have a neutron. I'm not sure. I think you should search that up. Maybe search that up and let me know in the comments. Right? It'd be nice to see if people are actually listening to what I'm trying to say. Because, I mean, most of it is just textbook, but also most of it is just me talking about what I know of or what I'm passionate about. So yeah, coming back, nuclei. If you know atoms, you should probably study nuclei, right? Because it's nuclei plus electrons that make an atom. It's good to know. The last chapter is XIV 14, Semiconductors. Semiconductor physics. It's a bit dry, personally speaking, but we could get through it. It's easy. It really goes into depth of what the electronic components in your phone are probably made of, diodes, transistors. You need to know all sorts of things if you go into engineering, but if you don't, well, just added knowledge. Semiconductors are created devices. Well, okay, basic definition of a semiconductor: it conducts just a bit. Conducts what? Conducts electricity. Copper conducts electricity very well. But does wood, does plastic, if I take this pen, connect to wires and a battery, it's not going to conduct. But semiconductors conduct sometimes, right? It's more like I can control the conductivity of it using chemical means, but we'll get to that later. They make devices out of it. Some of them are diodes, BJTs, I think, bipolar junction transistors. I think in the textbook it's just transistors. I'll get to that. I haven't been a big fan of this chapter, but I'll hope to cover it for you. Most of this is modern physics. Maybe that's not modern. Rest of it is. This is the whole problem we've been dealing with as well. Physicists have been dealing with photoelectric effect. You don't know if it's a particle or a wave. It led to the invention of, or maybe not the invention of, but the discovery of, or invention of, well, it led to a new field of physics, quantum mechanics. And you learn technically the birth of quantum physics, although it's not explicitly mentioned as such. But it's pretty interesting if you, but also, I think the first textbook is a bit more cohesive. It links all the topics perfectly within it. This one is a bit slightly more scattered than that one, but it does link itself into a good way. Now I can say these two are connected. If you know wave, you need to know wave, and then you know it's dual. You understand it's matter. You need to study atoms, nuclei, and you could study semi. It's not very tightly linked. However, I'll try my best to break it down for you. This is the easier textbook if you talk about, I think, questions, maybe theory-wise. It's a bit tricky to get your mind across, to wrap your mind around it, but it's okay. It's not challenging. You can easily get through this. So, that is the map of physics. Now we shall begin. Essential physics, but not in this video. I'm gonna make separate sectional videos, so it's not, I don't know, a 48-hour long video. It's gonna bore everyone out. And obviously take breaks, right? Don't just focus only on studying. I know a lot of students, even including myself, we were tempted, right? The more time you spend in studying, the better it is for you. It may be not the case. Study as much as you understand, and well, try to optimize your studying time and everything so that you don't fall behind on your lectures, but don't overexert yourself and just dry out on the inside. You're going to end up hating what you do. And maybe you may think, okay, just the 10th and 11th and 12th, and after that we go to university, we are good. Maybe, but it's always good to cultivate a good attitude and habit towards studying. So yeah, I'm just not gonna spend a lot of time on that, but here we go. Essential physics. That ended up looking like an integral. It wasn't on purpose. Well, the second time it was. But here we go. Essential physics for grade 12. Yeah, I'm just going to write that down so you don't get confused. I know it's just my handwriting isn't really great with this, but yeah, I will make it better when I'm writing down notes or derivations or questions or all sorts of things. Maybe I might even use a visualizer and paper if I could get access to it, but for now I'll be using the board. And welcome to Essential Physics. Thank you for watching.